This video is all about atoms and atomic structure. So atoms are the essential building blocks of matter. Antoine Lavoisier discovered the law of conservation of mass. Um, Interesting fact, he lived in France in the French Revolution, and he was actually beheaded in the French Revolution. He, was part of the tax scheme in France. He was not only good at meticulously keeping track of masses going in and out of chemical reactions, he was good at keeping track of finances and was part of this. He was kind of one of the masterminds of the very high taxation system in France before the French Revolution. So anyway, in his law of conservation of mass, he said that in chemical reactions, matter could be neither created nor destroyed. Now, all matter has mass, and so that meant that the mass couldn't be created or destroyed, and that the mass of the reactants had to be the same as the mass of products. For example, if hydrogen and oxygen are ignited, and it's usually very explosive to make water as a product, if you had 4 grams of hydrogen gas and 32 grams of oxygen gas, they would react to make a total of 32 plus 4 is 36 grams of water, and mass would be conserved. Dalton's atomic theory says that all matter is composed of atoms. Democritus was the first to coin this word, atomos, and he coined that word as indivisible or not divided into parts. So we'll get to that in a second here. But in Dalton's theory, the atoms of each element have unique characteristics and unique properties. Okay, so every element is unique, has its own characteristics and properties. In chemical reactions, atoms are not changed, but they can be rearranged, and they combine in whole number ratios to form compounds. When we're talking about whole number ratios, that's like 2 H's to every 1 O in water. Dalton's theory wasn't entirely correct. He did claim this idea of atomos, that the atom is indivisible. Now, others later found that the atom is divisible, right? We can kind of get rid of that so we can read. Later found that the atom is divisible, right? It has protons and neutrons and electrons, so it can be further divided into parts. So that part of the theory was later blown out of the water, so to speak. Okay, so next up in our historical tour of atomic structure, the atom is divisible. J.J. Thomson was the first to find particles. J.J. Thomson and others also proved that the atom had particles called electrons. He did a cathode ray tube experiment and found that the ray was attracted toward a positive plate and theorized that the ray had to be made up of negatively charged particles called electrons. So the electron was this negatively charged particle, much smaller than the atom itself. Ernest Rutherford discovered the nucleus and the proton in what's called the gold foil experiment. So in his gold foil experiment, Rutherford shot alpha particles. Well, actually, as graduate students, we're busy doing this. This is one of the times where it's pretty well documented that other students are actually responsible for a lot of the work and discoveries, as is often the case in scientific research. But there were these alpha particles being emitted out of a small slit. And they would hit the gold foil and then be deflected and measured, as they hit a screen. And what happened is a lot of the alpha particles went right on through the gold foil. But every once in a while, a particle was deflected straight back, either straight back at the back of the screen or deflected off on the side. And so that was pretty shocking. And because of that, Rutherford and his students were able to theorize that there was a nucleus in the atom, a tiny, dense central core. And so that every once in a while, if an alpha particle hit this very small, very dense central core, it would be deflected right on back. The nucleus takes up about only 1/10 trillionth the volume of the atom, so it's very, very tiny. It's actually almost incomprehensible how tiny the nucleus is. The nucleus is like a pea in the center, so like the vegetable, like the little green pea. It would be like a pea in the center of a large sports stadium. So let's say Allianz Field, if you're a soccer fan, or maybe US Bank Stadium if you're a football fan. But, imagine a tiny pea in the center of a huge field. But that tiny pea or that nucleus would essentially have the entire mass of the atom. So you wouldn't be able to just carry this item into the field, right? So just to give you an idea of the scale, so when we draw a nucleus here as a little dot that we can see in a circle we can also see on the screen, that's not the right order of magnitude, right? Any circle that we can draw on a screen or on a paper as an atom is going to have a nucleus that's so tiny that we won't be able to see that dot. But we just draw a dot there anyway, so we have some conception of what's going on. Okay, so it's like the pea in the center of a field. So the nucleus has this tiny, dense central, is a tiny, dense central core, only about 1/10 trillionth the volume of the atom. But it does essentially have all of the mass of the atom. And it contains the protons, which are positively charged particles inside the nucleus. So based on this experiment, we found out that we had a nucleus with the positively charged protons, and actually that the rest of the atom is actually mostly empty space. That was really remarkable. It's so remarkable. I'm going to write it down here. Empty space. That was really shocking that the rest of the atom is just mostly empty space. Okay. So Dalton was able to determine the relative masses of the atoms. He based his scale on a hydrogen atom having a mass of 1 AMU, where AMU stands for atomic mass unit. So it just needed a basis, picked hydrogen to be 1 atomic mass unit. We now base the scale on carbon-12 and say that that's exactly 12 AMUs, but it's the same big picture idea. I got it here, atomic mass unit, AMU or a Dalton. So now we know the atom is made up of protons, neutrons, and electrons. So the neutron was discovered as well. And the nucleus is going to have protons that have a charge of +1 and a mass of about 1 AMU. The neutrons have no charge at all, they're neutral, and they have a mass of about 1 AMU as well. So in the nucleus are these massive particles. That's where your mass comes from. 1 AMU each for the protons and the neutrons. Because outside the nucleus, we have these negatively charged electrons. They have charge of -1, but they have a mass that's much, much less than 1 AMU. Basically, the mass of the electrons is, for all intents and purposes, negligible. To give it a number, it's about 1/2000th of an AMU. So not quite 2000, it's 1900, but it's about 1/2000th of an AMU. So, we can just ignore, the mass of an electron because it's so tiny. We all but ignore it. Okay. So what do we need to know about these subatomic particles? I've got their exact masses listed here. We don't really need to know those. It's important to know that the protons and neutrons have a mass of about 1, right? So we could just go about 1 AMU. We don't have to know the exact mass. The electron has a really, really tiny mass, so that's just small. Or honestly, we can pretty much ignore that mass. Where are they located? Well, protons and neutrons are located in the nucleus. Protons are +1. And oh boy, that says the wrong thing. My electron should be negative. Well, that's embarrassing, but I'm going to just fix it. My electron should say -1, and my neutron should say no charge. We're just going to keep rolling because life's got mistakes. Just got to fix them up. Okay, so protons +1, electrons -1, neutrons no charge. We like to abbreviate them P or P plus for proton, E minus for electron, and N0 for that neutron no charge. Okay, so let's look at describing our atoms in a little more detail. So each element has a unique name, a symbol, and its number of protons. For example, potassium here has the name potassium, the symbol K, and it has 19 protons. So that's what we're talking about. Atomic number is sometimes called Z. I personally don't tend to call it Z that much, but it's been given the designator Z for the number of protons in the nucleus. And if we look at the periodic table, the big number in the top of an element box that's usually centered is that atomic number. That atomic number is really equal to the number of protons. That tells us how many protons that atom has, that element has. Then we've got the element symbol K, and then we've got its atomic mass. Lastly, down here, I mean, we were talking about its name, so we've got the full name written out too. Now, atomic mass is something that is an average, so we'll get to that in a second, but it's really an average atomic mass. So the practice asks, what is the atomic number of boron? Well, we got to get out our periodic table, and I got to erase this. We got to find boron, B, on our periodic table. So it's right here. And it says, what is its atomic number? Well, that's the one listed at the top, or the 5. By the way, that means it has 5 protons. That's what atomic number tells us. This is how many protons does a chlorine atom have? Well, we got to find chlorine. It's right here, and it's got a 17 for its atomic number. That means it has 17 protons. So atomic number determines number of protons.